Maybe we should get started. In the last lecture, we talked about representations quite a bit and various properties of representation. What is a representation? A Lie group is just a continuous. It's just a continuous group homomorphism. GL of V or vector space. The vector space is real or complex. And what is a representation of a Lie algebra? Again, Lie algebra homomorphism into the algebra GL of linear transformations on the vector space V with the usual matrix commutators. Okay. And then we call the representation irreducible if the only invariant subspaces that it has are the triple subspaces, which is 0 and all of V. What is an invariant subspace? It's a subspace of this vector space V, such that pi GW is contained in W for all G. And you also have a similar definition for the Lie algebra. Subspace for a representation of a Lie algebra, and then if such a subspace exists, that's called the subrepresentation. The original representation is called the reducible representation, and if no such subspace, no such proper subspace exists, then we can call the reducible representation. Yeah, and then we saw the concept of morphisms in the category of representations, or rather intertwining maps, which are maps between representations that commute with the actions. We have two representations V and W of a group G, and an intertwining map from V to W is a linear map that's shown diagram. The actions of all elements of G, all G. And then we also saw that any representation can be differentiated. We can have the derivative representation of a representation pi of G. Derivative is this pi under 9. We keep this notation throughout. And it's going to be a representation of the Lie algebra, fracture G of the Lie group G. Okay? And we also learned that if G is connected, irreducibility of pi and underlying pi are the same. Pi is irreducible if and only if underlying pi is irreducible. And again, for connected G, isomorphism of representations of G is the same as isomorphism of their corresponding derivative representation. More precisely, if you have two representations, pi 1 and pi 2, or maybe I have pi and sigma, if you have pi and sigma, then pi and sigma as G representations, capital G representations, are isomorphic if and only if their derived representations are isomorphic Lie algebra. Okay, so these are the things that we learned, right? And we also learned that we can always complexify a representation on of a real Lie algebra on a complex electric space. We get the representation of the complex algebra. Right? So these are the things that we discussed last time. Right? Maybe I should add that we have our midterm coming up after the reading week, which is next week. So next week there are no classes, and the midterm will be based on the material that is covered until the end of today. Okay, so the midterm will cover everything until the end of today. Yeah.
The midterm's in 3 weeks from today, right? Is that on the website?
Yeah, but let me. Okay, I will send the clear information about what's covered in the midterm.
It'll be 3 weeks from today, right?
So 30th, right?
Okay, so next week there are no classes, and the following week there are classes.
Yeah.
But the material on that week I don't want to be on the midterm. The week after.
Oh, okay.
So the material the week before midterm, it's not on the midterm. That's really the main point. So the midterm will cover until the end of today. Okay. And I will post a sample exam on Moodle, an exam that I gave a few years ago when I taught a similar course. You can use this as a practice exam. For students who are taking the course at other institutions than New Ottawa, you will receive your exam as an online assignment. Just the way you receive your assignments, you will receive your exam there, and you have to write your solutions and take a picture, like a scan, like a phone scanner app, and create a PDF file and upload. Okay? For you Ottawa students, the exam will be in person and it will be given in a classroom, just like the regular lecture. Okay? If there are any questions about the exam, please send me an email, or you can ask them now, or you can put them in the chat. All right. If there are any questions about the midterm? All is good? Okay.
Was that solution to the sample exam be given or?
Yeah, the sample exam has solutions, right? Yeah. Okay. Okay, so as I promised from last time, the goal today is to look at representations of a specific Lie group and understand them completely. The example would be the Lie group SU2. So this is an example, but this is a long and important example. Okay. So what is this as a group? It's the group of matrices such that they're 2 by 2. And A star A is identity. And the determinant is 1. We write the condition below. Okay. And you can give an explicit matrix realization of SU2 is the set of matrices of the following form: A, B minus B bar, A bar, A and B complex, norm A squared plus norm B squared equals 1. So this is really not difficult to compute from the above discussion. Okay, so that's an elementary calculation. So now I would like to describe a representation of SU2 on some n-dimensional vector space. In other words, I will give a representation pi m that goes from SU2 to GLMC, which is like GL of V for V and m-dimensional vector space. But the vector space that I give, I don't want to think about the vector space with like a standard basis. I want to think about it more as the space of polynomials homogeneous of a certain degree. Okay. In fact, why don't I actually shift my indices a bit with everything else? I would like to give the representation on an m+1 dimensional space. Okay. So this V, which I mean is like I call it VM also. It's basically the span over C of these monomials. Z1 to the M, 1 to the M minus 1, Z2, 2 to the M. So it's basically the space of complex, like homogeneous polynomials degree M with complex coefficients. Okay. Sorry, polynomials in 2 variables. So polynomials in 2 variables, Z1 and Z2, with complex coefficients and degree M. So every monomial here has total degree M, as you see here. The sum of the degrees of Z1 and Z2 is M. Okay, so for instance, I mean, V3 is the space of polynomials of the form A, call it like A0, Z1 cubed plus A1, Z1 squared, Z2 plus A2, Z1, Z2 squared plus A3, Z2 cubed. The dimension of VM. Okay, any questions so far? So this is going to be the vector space, and I want to realize this representation as linear operators on this vector space. Doesn't matter what vector space I choose, because all vector spaces of the same dimension are really isomorphic. But it will be easier to look at things in this picture. Okay? Any questions so far? Is it clear what vector space I'm talking about? So now the action is as follows. So the action is really the following. So if G is in SU2, and the elements of this VM really are, polynomial functions. So maybe I just use the letter F because it's a function, right? It's a function in two variables. And now I define the action. Maybe I just write pi m e of F. So I should tell you what linear transformation on VM it is. So I should tell you what this pi mg does to F. Okay? Well, this is not supposed to be a function again of this z, where z is just the ordered pair z1, z2, right? Function of z1 and z2, and yeah?
On Z1 and Z2.
In principle, so it's f of g inverse, where what does this mean? Well, g is of the form a b minus b bar a bar. Z really is this vector, is z1, z2. I write it as a column vector. So now G inverse Z. So what is the inverse of this matrix? I have computed it. This is going to be a bar minus b, b bar a. You see that the product of this matrix and this matrix is going to be the identity matrix because of this relation, a bar squared plus b bar squared, like a absolute value of a squared plus absolute value of b squared. Right? And so z is just this z1, z2. You end up with this formula, a bar 1 minus b z2 and b bar z1 plus a z2. More precisely, if I wanted to write this explicitly, I should write f of maybe I just write here equals f of a bar z1 minus b z2 b bar z1 plus a z2. Okay. Now, from the way this action is defined, it's not difficult to see that I have a representation. First of all, why is it a linear map? So it's pi m g of like C1 F1 plus C2 F2. This is like, what is the value at Z? The value at Z is C1 F1 plus C2 F2 of G inverse Z. But you have a linear combination of functions evaluated at the same point. So you could write it as C1 F1 G inverse Z plus C2 F2 G inverse Z. And in the end, you just get C1 pi mg F at Z plus C2 pi mg F2. Okay? So this means that pi mg acting on this is the same as pi mg C1 times pi mg acting on F1 plus C2 times pi mg acting. This proves linearity of pi m. Mg. Okay. Okay. And we also need to verify that this pi m is a group homomorphism. I'll check it shortly. I need to check that pi m of G1, pi m of G2 is pi m G1, G2. And that is where this inverse comes into the picture. You might say, oh, why did you put this inverse? Why didn't you just put G? But this inverse becomes important when we do this calculation. Otherwise, we wouldn't get this relation. So let's see why. So pi m of G1, G2, F at Z. What is this? This is F of G1, G2 inverse Z by definition, right? And this you can write as F of G1, G2 inverse, you can write it as G2 inverse G1 inverse Z. And remember, Z is a vector, so it's all by matrix multiplication. It's like I can expand it like this. But now F of G2 inverse of something, that is let me see. G2 inverse. Okay, maybe I should start from the other side. Maybe it's easier to do it the other way. When you look at like pi m G1 of pi m G2 F at Z. Let's see what this is. So this is pi m G1 of this guy. Maybe I call this H for the moment. So this is pi m G1 H at Z. So this is H of G1 inverse Z. Okay, but what is H of something? So H of Z in general, this is like pi m G2 F at Z. So this is F of G2 inverse Z. Okay, so now looking at this, H of G1 inverse, if I plug G1 inverse here, I end up with H of G1 inverse. Wait, so I need to plug in, right, so here I need to set, like I need to plug in G1 inverse G2, G1 inverse Z, sorry. Z instead of Z. So then I get F of G2 inverse G1 inverse. Okay, so the last thing will be, using this lower relation, I get F of G2 inverse of G1 inverse, which is the same as this guy. Okay. Now, if I didn't put that negative sign, it's negative in the exponent, then this thing wouldn't work out. I would get something like pi m of G2, pi m of G1 equals pi m of G1, G2. It will not be homomorphic. It will be like from the opposite. All is good? Okay. All right, so now, okay, so maybe I just say the proof that I have a group homomorphism. So I just define this group homomorphism, right? And now, so the claim is that this representation that I just constructed, this pi m, or all non-negative integers, it makes sense. This is the unique, irreducible SU2 representation of dimension m, of dimension m plus 1. Okay. So now, how can we prove this assertion? But the proof is, well, it's not totally trivial, but I'll explain some of the ideas of the proof, like maybe like at least the fact that these guys are reducible. So now that you have this group representation, of course, you just like any group representation, you should ask what is the corresponding Lie algebra representation? Because the Lie algebra representation is supposed to be much easier, right? Because like it's a linear map. So it's supposed to be something at the level of linear algebra. You don't need the complex group theory involved. Okay, so let's compute the pi m underline then, right? That's our next goal. Okay, so SU2 is the Lie algebra of this group SU2, which is the set of matrices by 2, such that x plus x star is 0, and the determinant condition turns into a trace condition that we've seen before. Okay, it's co-Hermitian and trace 0 matrices. Okay, so now how do we differentiate this representation? We just have to take one parameter subgroups and then differentiate at 0, right? So we take so pi m underline x of f at z. This is what we want to compute. So this is for f in Vm. Okay, and x in the Lie algebra, which is SU2. Okay. So what is this? This is the derivative at t equal to 0 of pi m of e to the tx f at z. Okay. The differentiation really commutes with the evaluation at that point, right? And so this is really d dt. But well, I mean, this pi m was supposed to be just applying the G inverse and evaluating. So this is d dt at t equal to 0 of f of e to the minus tx, which is the inverse of e to the tx. Okay. So now this is calculus, right? So now you could say that if I set et to be e to the minus tx z, okay, where z was like z1, z2, some point, maybe I should put maybe a bar here. I don't know. I just want to make sure that you understand these are not variables anymore. These are just some, like, this is some fixed point. Yeah, z. If I put tilde here. Okay. So then, what is the derivative here? So I want to differentiate this. Okay, so what should I do? Well, this is a composition of functions. I should use the chain, right? So I should differentiate f, find the derivative of f, and then compose it with the derivative of the inner thing. So I'm doing calculus, right? So maybe in terms of partials, maybe I should continue this calculation first and write the next thing. So I have df dz1 times d z1 dt plus df dz2 dz2 dt. This is just the chain rule of calculus, right? But what are z1 and z2? z1 and z2 are just the coordinates of this. So I just write this as z1 d. Okay. And when I differentiate these guys, now it's not difficult to see what it is, because when I differentiate this, so this is the derivative of an exponential, I get this minus x. Okay, so just right here. So dz dt is minus x e to the minus tx d tilde, and I want to do this at t equal to 0. I end up with minus x d tilde, okay? And if I write x as a matrix x11, x12, x21, x22, I end up with this formula as minus x11 z1 tilde minus x12 z2 tilde. Maybe I'll just write in the next line. It's like this minus x11 tilde minus x12 z2 tilde minus x21 z1 tilde minus x22 z2 tilde. Okay, so now coming back to here, now I can make substitutions for these derivatives. Okay, so these inner derivatives are supposed to be done at t equals 0. Oops. Okay. So now I have computed. So I have computed these two quantities. This one and this one. The dz1 dt and dz2 dt. They are basically these formulas. Okay. And they are expressible in terms of the z1 tilde and z2 tilde. So what I get is the following. Maybe I just write in the end a bit lower. So I'll just write, so it follows. I am underline x. F at z. Now this formula when it was written in terms of the tildes, but I'm really evaluating at some point z1. So here z1, z2 could be the point that I'm plugging in. Okay, so then I could just write this instead of these coordinates, I could write these guys without the tildes. Okay, so I will obtain minus df dz1 times minus oh, I'm sorry, so there's no minus here. x11 z1 plus x12 z2 minus df dz2 x21 z1 plus x22 z2. Okay. All is good so far? Everybody following? Right? I just hesitate to change this font size because then I end up writing bigger and then it will all look way bigger. But anyway, okay. I should just keep this the way it was. Just scroll to the left or to the right. Okay. So now, for any matrix in this Lie algebra SU2, I got this formula, but this formula is really linear in these coordinates. In the coordinates x1, 1, x1, 2, x1, and x2. Okay? Therefore, I can extend this to the complexification. Okay? So we can extend formula to the complexification of SU2, which we learned was just SL2C. And now SL2C has again this important basis that you should never forget. It's the basis of the matrices like this. this. And like this. And now I can still plug in the entries of these matrices in the formulas for the pi mx. Because even though these matrices are not in SU2, they are in the complexification. So I could just say like pi m of x plus iy. I could have had something like x plus iy would have been pi m of x plus I times pi m of y. I could have expanded this linearly, right? I'm just complexifying everything to get the representation of the complexified Lie algebra. Okay? And so then the formula that I get will be very nice. So for this one, so pi mh will be this differential operator minus z1 df dz1. So I just write it like that. I don't put the f anymore. You just plug in f and you get this the action, right? Minus z2 ddz2. And for E, it will be this operator underlined, sorry, so pi mx is minus z2 dz1 and maybe I should write E here, sorry. IMF is minus z1 dd. Okay, so now some of you might know what these operators are. What does this operator do, for example? Apply it to a polynomial in Z1 and Z2. What do you expect? Differentiating respect to Z1 and then multiplying by Z1. What happens?
It's by a constant.
Yeah, and what is the constant? So think about this operator, like the x ddx operator. What does it do to a polynomial?
Clears out the constant, so it remains homogeneous.
Okay, so like what is it?
And
No, x
Huh?
times
This is n times.
x, yeah.
That's right. Okay, so what this means is that, in fact, the xn's are somehow eigenfunctions, or rather like the eigenvectors of this operator, right? And in fact, the eigenvalue is the degree. Okay, same thing happens here. So if you plug in a homogeneous polynomial here, it will be an eigenvector, and the eigenvalue will be minus the degree. Okay, but now, okay, I just realized that I had a mistake. So in fact, I shouldn't have said all of this. I just had a sign error here. Not exactly. There's a plus sign. What I said was correct, but I forgot about this. The sign changed. So now the picture is a little bit different. But still, what happens is that the degree of Z1 and Z2 will not change. In other words, the monomials Z1 to the K, Z2 to the L will still be eigenvectors of this operator. But this time the eigenvalue will be something like minus K plus L. Right? Because this will give you a minus K, this will give you a plus L. Just like that, what I showed you for X ddx. Okay? Right? And now what about the same monomials when you plug in those monomials here? If you plug in a monomial, the degree of x, the degree of z1 goes down, the degree of z2 goes up. And here it's the opposite. Okay? So the formulas, I'll write the formulas explicitly. I am h of z1 to the m minus k, z2 to the k is minus m plus 2k k. So it will be just minus this exponent plus this exponent. That's why you get this minus m plus 2k. And what is the range of k, by the way? The range of k would be between 0 and m. And pi m e on the same monomial will be minus m minus k z1 to the m minus k minus 1 z2 to the k plus 1 pi m e, sorry, and pi m f minus k z1 to the m minus k plus 1 z2 to the k minus 1. Okay. So now, working with the Lie algebra action is much easier now, because now at least you know that this operator is diagonalizable. And these guys are moving around the eigenvectors. Okay? So what this means is that we could write this picture, say, we put Z1 to the M, maybe I put Z1 to the M here. I put Z1 minus 1, 2. Yeah, maybe I just need a bit bigger gap, sorry. I put Z1 to the M, and I put Z1 to the M minus 1, Z2. Up to Z1, Z2 to the M minus 1, and finally Z2 to the M. These are the spanning monomials, right? And we know that this H guy, diagonal, so maybe I represent this by these arrows. So each of these vectors goes to itself by some eigenvalue. And the eigenvalue, if you look at this formula for pi mh, you see that the eigenvalue here is m, then you get m minus 2, and then you get finally minus m. They go by units of 2, steps of 2 units each time, and from between m and minus m. Okay, now what about these operators E and F? So the E increases the Z2 degree, the E goes in this direction. This is for H. These are the E's. The E's will push vectors upwards, and last one will go to 0. Okay? And the F's push vectors downwards. Different color for the F's. The last one will be annihilated. Okay? Are you guys following? Is it clear? Okay, no? Not at all clear? Let's look at it out. So, okay, so let's just do the case m equals 3. In this case, the basis will be Z2 cubed, Z1, Z2 squared, Z1 squared, Z2, and Z1 cubed. So now, this is an eigenvector for H with eigenvalue 3. This is an eigenvector for H with eigenvalue 1. This is with eigenvalue minus 1, and this is with eigenvalue minus 3. And now, looking at this formula, what is pi 3e? Is it pi? Yeah, it's pi 3. Pi 3e for the first vector. For the vector z1 cubed. From this formula, we can compute it, right? So pi 3 e of z1 cubed, it's supposed to be minus 3 plus, so z1 cubed corresponds to k equal to 0. So it can give you minus 3 times z1 squared z2. So this E maps this vector to this vector up to some scalar. And same here. It maps this vector to this vector up to some scalar and this vector to this vector up to some scalar. There are some scalars which I'm not writing right. And the last one, of course, will go to 0 under E. Because if you look at it, E, what does E do? E is supposed to differentiate. You can look at the formula, but you can also look at here. Where's the formula for E? It differentiates with respect to Z1. If there's no Z1, it should annihilate the function. Okay. The same with F. If there's no Z2, then F will kill out that function. Okay, so then this F will actually kill this guy.
So it's not invertible?
This is the Lie algebra action. It's not supposed to be invertible even. Okay, the Lie group version is the exponential of this. It will be invertible, but not the Lie algebra. Okay, all right. Let me see. There's a question in the chat. Okay, so the fact that the eigenvalues are integers, yes, that is interesting, and there's a meaning to that. There's even a physical meaning to that. So it's even related to particle physics, sort of the states of the hydrogen atom and so on, the energy levels and so on. So physicists interpret this when they sort of describe subnuclear particles. But from a mathematical point of view, it's related to some integrality condition that is there in the theory of finite dimensional modules of semi-simple Lie algebras. So there's a characterization of modules of semi-simple Lie algebras by, this basically goes back to the work of Cartan and Weil. It's called Cartan-Weil theory. And basically, you characterize representations by linear functionals on the diagonal subalgebra, so to speak. So here the diagonal subalgebra was spanned by H. In general, you have a diagonal subalgebra of your simple Lie algebra, and then you take linear functionals on that. And the condition should be that there's some sort of dominance plus integrality. So yes, this is like a special case of a more general property which is very well understood. Thanks for asking this question, Mohan. But from this picture, you could expect that it. Okay, so let me explain maybe in simple terms why this integrality should hold. So integrality should hold because so if you had some H eigenvector, so HV was lambda V. Now, if you apply this, say F to V, let's see what is HFV. This is F HV plus. Well, this is like HFV. I'm just using the Lie algebra relation, the bracket of H and F. Okay, but what is HF? It's minus 2F. So this is going to be F times HV, which is lambda FV minus 2FV, which is lambda minus 2FV. In other words, F pushes eigen vectors down in units of 2. Okay, and E pushes them up by units of 2. In other words, the eigenvalue should go up by 2 units under E and should go down by 2 units under F. Okay, and yeah, so that's really in principle the reason. Because after all, the algebra module should be generated by one vector and the action of these and the F's. If you have some lambda, then the shift should be integral. Okay, any other questions? All right, so now here is the proposition. That for every integer m non-negative, Im on this Vm is an irreducible representation it's U2. Okay, so let's prove this assertion. So the proof, I'll give the sketch of the proof. I don't want to like complicated details. So what's the sketch? What's the idea? The idea is more important than like little details. Okay, so maybe you want to listen carefully about like to learn the main idea. So first, SU2 is connected. Therefore, it's enough to show that pi m underline Bm is irreducible as a Lie algebra SU2. Okay, so now suppose it's this module is reducible. How can this happen? So there's some proper invariant subspace. Okay, now let's look at this picture. I'll just draw these dots that represent these vectors with these H action and so on. So take a vector in that subspace W. W is some proper subspace that's invariant under the Lie algebra action. Take a vector. That vector is a linear combination of some of these vectors. Maybe this kind of, with some weights. Okay. So now you apply this E operator that pushes all the points 1 unit to the right. And you can see from these formulas that the coefficient is non-zero all the time, except for the last step where the vector dies. So if you have a linear, like if you have a vector in W, you push it to the right, the coefficients change by some non-zero scalar. In other words, if they were non-zero, they will not die still, unless they are pushed off the limit. Okay, so you try to apply the E to push this vector, and it still remains in W, right? Because this is W invariant. This is like a little fracture G invariant. It's W. Okay, so you push these guys off the limit. So first this one falls off, and then this one falls off, and this one survives, right? So now you could push it as far as this one gets to this point. Okay, so now this means that a scalar multiple, a non-zero scalar multiple of this last vector, which was I think was it z2 to the m or z1 to the m? It was z2 to the m. A scalar multiple of this vector will belong to W. So you can assume z2 to the m is in W, right? And now you push back via f. This is in W, so you push back via f. So this means that all other vectors which are now obtained by pushing this via f to the right are also in W. Therefore, a basis of V is contained in W. Okay? So this was some kind of a, maybe this argument is better explained with the picture rather than with complicated formulas. Is it clear what I said? So I said take a vector. Should I explain the argument again, or is it clear? You want to explain again? Anybody wants to explain again? Yeah. Okay, so let me explain it again. Okay, so take so maybe so first this part I hope is clear that I just reduced it to the Lie algebra version. I just need to show that the Lie algebra representation, this Lie algebra SU2 representation is reducible. Do you agree with this part? Okay, everybody happy? All right. So now take some vector in W, the little w, like some little w in W, and suppose that that vector is a linear combination of a bunch of these points, which are the basis vectors of V. Okay. Apply F. So in other words, you consider this pi f W. I'm sorry, this is E. So pi E goes in this direction. Then you do like pi E squared W and so on. They are all in W, right? And when you push them to the right, as I said, the new vector pi EW will be a linear combination of say this, and this, because each of these vectors will be pushed 1 unit to the right. And the weights, if they were non-zero, will remain non-zero. That is clear from the formula, because the scalar that is multiplied here is the... No, I think something is frozen. You see it? Anymore? Let me stop sharing and share again. Just close one note and open it again. Okay, now it's moving. And now let's see, there are some questions in the chat. Okay, yeah, Mohan, you certainly know quite a bit of physics when you say this. Okay, so that was a physics comment about the quantum magnetic numbers. Yeah, they're certainly related. Spin values of particles anyway. But anyway, okay, so let's continue. So suppose that the vector W was a linear combination of this, this, and this. Now, pi EW will be linear combination of the vectors immediately to the right of the circle point, which means this. Okay? And pi E squared W will now be a linear combination of this, and for this one, this will fall off. So this will be only 2. And if I apply this pi E one more time, this last one will fall off. So eventually I will only left with a linear combination of one of these bases with a non-zero coefficient. Okay? And eventually by pushing this to the left, I can assume that this first vector, which is Z, again I forget, is it Z2? Yeah, Z2, M is in W. It will be some pi K. So some pi K, so some pi E to the power KW will be either Z2 to the M or some scalar multiple of some nonsense. Okay? And now you start applying Fs. Okay, so again, if maybe I just erase coloring things. Okay. Now I know that this vector is in W. Okay. Applying F will tell me that this vector or a scalar multiple of that is in W, and that scalar is non-zero. Again, by looking at the formula for it. And you continue, like then this vector is also in W, and this vector is in W, and this, and this, and this. So everything is in W from the basis. Okay, is it all clear? Now, you need also to show that there are no other irreducible modules. And that is a little bit harder to show, so we'll skip that argument. Really, the modules that I showed you are the only irreducible finite dimensional modules of SU2. Or equivalent to the algebras. Okay? Any questions before we continue? All is good? Everybody happy? So let's move forward with looking at representations a little bit more. So given two representations, we can form a direct sum of the two representations. Just like the way we form direct sum of the algebras, we can form direct sum of representations. So here's the definition. You can do a direct sum of two or more representations. So let's do the general form. G and the matrix Lie group. And let pi 1 to pi m be notations of G on vector spaces V1 to Vm all over R or all over C. Let's not mix them up. Okay, so then the direct sum of I1 by M, which I'll define momentarily, is also a representation of G on the vector space V1 up to plus up to Vm, the direct sum of the vector spaces, where pi G, so like pi1 plus pi M G as an operator on the direct sum. It should like act on the vector which is the direct sum of the components, right? It will be just pi 1G V1 direct sum pi mg. So it will be acting on each component separately. Okay. In other words, if I choose a basis for the direct sum space that's compatible with the choice of the VI, which means first a basis for V1, then a basis for V2, so on up to a basis for Vm, and I write the matrices for pi mg in this basis, what kind of matrices do I get? Right? Huh?
Or block diagram.
Exactly, I get a block diagonal matrix, with the blocks being the matrices that I got for pi 1 up to pi m. This is pi 1 plus pi m of g. This is pi 1g, this is pi mg. And you have zeros elsewhere. This is block diagonal. And what happens for the Lie algebra? For the Lie algebra, it will be the same thing. So I1. So for if G, so or maybe okay, maybe I should say the associated Lie algebra. Is pi 1. Pi m is again just a direct sum of the derived representations coming from the Euclid representations pi 1 to pi m. Again, pi 1 underline plus pi m underline x acting on V1 plus Vm is just simply pi 1 x V1 . Yeah. Okay. How many people are familiar with the concept of a tensor product? You familiar with tensor product? Yeah. Vector spaces only. Yeah. Are you familiar with tensor products?
Know a little bit of the vector spaces, but
Okay.
like I read about the definitions, but I haven't used it a lot.
Okay. So people online, Mohan and Jenny, are you familiar with tensor products? Okay, it's okay if you're not, but I say it's going to be some, maybe you could consider this as extra material. Okay. So you can always tensor, so this is extra material. So you can also tensor two representations of a group. So given I1 V1 and I2 V2, two representations of a matrix group, but in general any group G, you can form the tensor product station that's we will denote it by pi1 tensor pi2, and it should. We can be, I mean, it's enough to describe what it does to a tensor. I mean, not every vector in this tensor product is of this form. So what is this tensor product? We have this tensor product vector space. V1 tensor V2. The elements here are not all of this form. They are linear combinations of this form. But these guys span the tensor product, and therefore it's enough to describe this action on just the spanning set and then extend linearly. Okay? And it will be like pi1 x v1 tensor pi2 g. Okay? Maybe I should say on v1 tensor. Vector space of the tensor of the tensor representation is the tensor product. All right. But now, what about the Lie algebra action? So the associated Lie algebra representation. So pi1 underline tensor pi2 underline x for x coming from the Lie algebra G on some tensor like this. What is it? Guesses? It will end up being pi1 x v1 tensor v2 plus v1 tensor pi2 x. It's not going to be pi1 x v1 tensor pi2 x v2, unlike the group version or the direct sum version. What is the explanation? Can you explain this? So how do we get the Lie algebra action? Well, we have to differentiate something, right? So we have to look at pi1 tensor pi2 of e to the tx applied to v1 tensor v2, right? We have to look at the derivative of e to the tx v1 tensor e to the tx v2 at t equal to 0. But now, again, we have this Leibniz rule, right? This is like, it's like we have to use a product rule. We have to differentiate this and evaluate at 0, plus evaluate at 0 and differentiate this. Right? It's like a product rule we have to apply, because this is a bilinear map, it's not direct sum. And when you do that, when you differentiate this one, it will give you the xv1, evaluate at 0 will give you this, but now you have to evaluate at 0, it will give you v1, differentiate at 0, xv2. Okay, so it's a natural consequence of the definition if you do this correctly. Okay, maybe I'll just erase this explanation. Because as I said, this is some external. Okay? You don't need to know this for your exam. I think it's just for like getting further knowledge of what's going on.
So the tensor will act like a product to the.
Yeah, what do you mean?
Like when you differentiate the pi1 tensor pi2, we got that result because the tensor is kind of like a product.
Okay, but yeah, well, I mean, the thing is that the tensor is a bilinear thing. So yeah, it's a question whether when you multiply two functions and you differentiate, you should think about this as, this is a map taking f and v to fv. It's a bilinear map versus when you do FG to F plus, like F direct sum G, this is linear.
Oh,
There's a
okay,
difference between a bilinear map and a linear map.
okay.
Okay, and so the derivative of something which is degree 2 and something degree 1 are really different. So the difference comes from there. So now, again, I will continue this example of representations of SU2, but I'm going to use some tensor things. So it's really not important if you don't know tensors, but just to show you some important things anyway. So let's now consider the tensor product of this. So this two-dimensional representation. Maybe I call it like a V1. Remember, V1 is isomorphic. So V1 is isomorphic to C2 as an SU2 representation. So we can form now V1 tensor V1. Which is as a vector space, this is C2 tensor C2. What is the dimension of this vector space? When 4. When you tensor vector spaces, the dimensions are model. Okay. Pardon?
Over C.
Over C, that's right. I'm doing tensors over C. So now, this is also a representation of SU2 by what I showed you above. Which representation is it? Is it going to be the V3, which is the 4-dimensional representation?
Who knows? Could be some sums of smaller representation. Anything.
Okay, and now do you know what's happening?
Okay, so
So the point is that here there's a natural decomposition as two representations. That will be the symmetric, maybe I write it as S2C2, and then the other one is H2C2. So what are these? This is the span of symmetric tensors. This means the span of E1 tensor E1, E2 tensor E2. And so let's say C2 has a basis E1, E2. And now here you have E1, E2 plus E2, E1. These three vectors span the subspace of symmetric tensors. And then there's another tensor, E1 tensor E2. Minus E2 tensor E1, that will span a one-dimensional subspace. And you can see that these subspaces also will be sub-representations. They will be invariant under the action of SU2. In other words, okay, I should have written V1, not V2. Okay. In other words, it decomposes as V2 plus V0. The one-dimensional plus the three-dimensional. Okay. And more generally, we can also describe Vm tensor Vn. It will have like Vm plus n minus 1 plus Vm plus n minus 3 plus da 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 to some point. Okay, it will like if m minus n if I'm not mistaken, but anyway. So there is some decomposition like this, and this decomposition is actually useful in quantum information theory. This is called the Clebsch-Gordon formula. And if you think about these as like Vm and Vn as spaces of qubits, this is some kind of decomposition of that space, which has value in understanding in like doing suitable measurements and so on. A bunch of things in quantum information, some kind of providing some estimates or noise tolerant computation or whatever. Okay? So it's useful in quantum information. How much time do we have? Okay, we have maybe 5 more minutes. Yeah.
we have the tensor products of the representations of SU2 are actually direct sums of irreducible. You have an analog of Mashka's theorem under modulus and hypotheses for these groups.
Mashka's theorem, which states every module is completely reducible? Yes, I mean for any compact topological group, representations, irreducible representations are finite dimensional, and every module is a direct sum of modules. Yeah. This is like standard. It's like it's called Peter-Weil theorem. Okay. Any other questions or comments or anything? So the last thing I wanted to say today is an example of a non-linear Lie group. All the Lie groups that we saw were matrix Lie groups. So now here's an example, a Lie group. That is not a matrix Lie. Okay? So recall that the Lie group was supposed to be a manifold with a group operation which was a smooth, multiplication and inversion very smooth. Okay? Now, whatever definition you want to take for a Lie group, the following example seems very natural for that, and then I'll show that this is not representable by matrices. So what's that example? Let's start with this matrix Lie group, the Heisenberg group. 1, 1, 1, 0, 0, 0, A, B, C, in A, B, and C in R. This is a matrix Lie group, okay? And what is it topologically? It's topologically, no, maybe I mean as like a variety, it's like a manifold. It's just R3 because I have three parameters A, B, and C. You can identify them with three coordinates. You can see this is really R3, homeomorphic to R3. So now I'd like to take this subgroup N, which is the set of matrices of the form 1, 1, 1, 0, 0, 0, 0, N, 0, where N is an integer. Okay. You can see that this N is contained in the center of H. It's not difficult. And in fact, H, and therefore you can form this quotient. Now, this factoring by N only affects the, like, you can think about this topologically as R cross R cross R. It's not the same as this Cartesian product as a group. This H is non-abelian. This Cartesian product is abelian. But I can at least topologically think about it that way. And then factoring by this last component, like factoring by this really means I have this R factored by Z, right? Because this only occurs in this last component, okay? And what is this? R divided by Z, topologically, what is it? So I have the real line, and I have taken the quotient by this.
The half open interval.
Yeah, but maybe a better description. I mean, how do you do this? I mean, you just wrap it around to identify. You have to identify these points on these line segments.
Yeah.
So you basically get a circle. As a group, you really get a circle, right? So topologically, you could say that this is R cross S1. This quotient, H mod N, sorry. Okay. So it's a quotient by this discrete subgroup. It's like a nice group which has a manifold structure. Really, that's what it is. But it turns out that it is, I mean, it deserves to be called a Lie group, but it turns out it's not a matrix Lie. So here's the claim. Maybe I state it as a theorem. So let phi from H to GL V representation of H on a finite dimensional vector space, complex vector space V over C, let's say, it doesn't matter. So if a kernel of phi contains N, then kernel of pi contains all of the center. Okay? In other words, I cannot have a faithful embedding of H over N into GL, because that embedding, it's just some homomorphism of H into GLV with N in the kernel, so the whole Z should be in the kernel. That's a corollary, so the corollary that H mod N is not a matrix Lie. Because if it was a matrix Lie group, then we would have some embedding of this into some GLV, which means we have some group homomorphism from H into GLV with kernel exactly N, but that contradicts the theorem. Okay. Everybody happy? Right. So how do we prove this theorem? Maybe okay, maybe, okay, I mean, the proof is longer than 4 minutes, so maybe I can stop here, so proof for next time. After we come back from reading week, I will explain this argument. And after that, we will move on to sort of explore things about, not like Lie groups which are not necessarily matrix Lie groups. The first thing that comes up is a formula that describes the relation between the group operation and the Lie algebra bracket. So in other words, sort of a prototypical example of that is how do you describe e to the x, e to the y as something in terms of x and y? It is not e to the x plus y in general, but there's some complicated formula called the Baker-Camper-Hausdorff formula, which is a power series. And that power series is extremely important in understanding the connection between the groups and the algebra. It's like basically a gateway to the theory of formal groups. Okay, so maybe we stop now and let me see, there are questions in the chat. Answered. Okay. I'll provide more precise information about the midterm, but basically that's by the end of today. And yeah, I'll post the sample examples.